Thank you, Mike. So something about new materials. How does that relate to the topic of this workshop? Well, I want to get to quantum computing, and then I want to get to green tech briefly, very briefly, and I need to talk about materials. That's actually one of the most exciting fields right now. There's quite interesting ideas floating around. Okay, let me see. Sounds like new materials. So let's start with new materials. So there's a new field being born, computational material science, which is data-driven and uses computers to simulate new materials, to calculate properties of known materials and unknown materials, and materials that don't exist yet, but could possibly exist. So materials project, which is done mostly at Lawrence Berkeley National Laboratory, is a non-profit institution that is doing this kind of research. Now, graphene has been around for a while. The first sheet of graphene was produced 20 years ago, and IBM demonstrated graphene wafers in 2010. All the excitement is because it's such a conductive material. It's very thin, very light, very strong, 200 times stronger than steel. Carbon is non-toxic in the body, and life is made of carbon, so carbon-based materials could be used to build little robots that travel inside the body and deliver a drug to a specific site. Microchips that made of graphene could fit many more transistors than silicon, and so on. Lots of exciting properties. The challenge is that graphene is a gapless material, which means it's more similar to a metal than to a semiconductor. I'll say more a little later. And the excitement in these days is for magic angle graphene that was discovered by Pablo Hajillo Herrero at MIT. He twisted 2 layers of graphene, or 1 layer on top of the other, and realized that that's a robust superconductor. And there's a magic angle at which this superconductivity peaks. And then David Goldhaber Gordon at Stanford realized that this twisted graphene also have magnetic properties. And then again, Hajillo Herrero showed that you can turn on and off the superconductivity in this magic angle graphene. So this gives us the dream of very fast, energy efficient, superconducting transistors. The cost of producing graphene has dropped substantially. Now it's less than $50 per kilogram. We still cannot produce graphene on a large scale without losing its properties. And the same is true of carbon nanotubes that were the wonder material of the 1990s. So the real goal is, how can we mass produce graphene? And here I listed some of the scientists that are working on this, solving this problem. Graphene-based electronics is a reality. There's a startup well-known startup in England called Paragraph that makes graphene-based electronic components. There was one in San Diego. It was acquired by Paragraph. And then there's research in different universities. I mentioned 2 of the most famous scientists in this field. Now, graphene is a 2D material. It's atom thin, so it's basically 2-dimensional. It is popular because of the fascinating properties, but as I mentioned, it has a problem. The lack of the electronic band gap doesn't make it an ideal semiconductor. And so there is research for two-dimensional materials with semiconductor properties. And one such material introduced last year is transition metal, I cannot pronounce it, dechalcogenin, and TMDC. That's a semiconductor with electronic band gap. And Samsung and University of Chicago also showed a method to fabricate TMDC transistors on a wafer scale. So there's more than graphene. Two-dimensional materials include graphene, but then there's also metals like TMDC, which, there's many TMDCs. On this slide, I mentioned the most popular. And then semiconductors like MOS2, insulators, we'll see this HBN soon, and so on. And it has been shown that 2D materials can be combined in one vertical stack, and the layers are held together by van der Waals forces. These are well-known forces. And what you get is called a heterostructure. So you can integrate graphene, TMDC, and so on. Each of them has slightly different properties. So I mentioned the HBN that has a large band gap. It has properties that make it interesting. It's ideal for the construction of these heterostructures. And if you combine graphene and HBN, then in these heterostructures, then you get something that is very close to having graphene-based chips. So this would give us the ability to build atomically thin chips, very, very, very small chips. So this in general is the topic of metamaterials. Metamaterial is a material that doesn't exist in nature with electromagnetic properties that are interesting to us, and properties that derive from its structure rather than from its chemical composition. I will mention U-carbon, which is magnetic, unlike graphene, and it's a promising material for biosensors, for vectors that deliver medicines inside our body. Julia Greer at Caltech works on what she calls responsive architected materials. These are artificial materials that can evolve over time, and a possible application could be neuromorphic computers. 3D printing has been around now for, I don't know, 40 years. A few years ago, they started building homes using 3D printers. But so far, I saw an article that only 130 buildings larger than 10 square meters have been 3D printed in the whole world. And 55 of them were done last year. And the problem is so for homes, the problem is that they're built with concrete, but the 3D printer cannot put down the steel beams that support multi-story buildings. And so homes are basically limited to one floor. In general, wood and metal filaments are still the most used materials. So these are limitations. At the University of Notre Dame, a team at the University of Notre Dame came up with this new kind of 3D printing that could make a difference, but that's very, very new and very tentative. So concrete as a problem, it is not eco-friendly. And so a number of places are working on hard, solid, wood-based materials. The MIT introduced one, Desktop Metal introduced one based on sawdust, and Pierre Laborie at Freiburg University also introduced one. Now that we discussed new materials, let's get into superconductivity. superconductivity was discovered more than a century ago. In the 50s, there was already a theory proposed by John Bardeen and others. John Bardeen is also one of the inventors of the transistor, to explain what causes superconductivity. Although there was still that theory was not complete. The dream, of course, I mean, superconductivity was discovered at a temperature that close to absolute zero. In 1986, two Swiss scientists at IBM discovered what they call high temperature superconductivity. Don't think of a high temperature as tropical hot. It means that it's not absolute zero. It's a little more. The room temperature is way higher than what they call high temperature in the world of superconductivity. 1997, Philip Anderson came up with another theory to explain high temperature superconductivity, and we see that for more than 30 years it was just a wild hypothesis. So then 1997, somebody finally discovers proves that there is superconductivity at a higher temperature, still very far from room temperature. And at that point, the main class of so-called high temperature superconductors becomes copper oxides combined with other metals, like the famous YbCO. Then again, in Switzerland, they discover a new superconductor, the cuprate of mercury, barium, and calcium. And that again creates a new interest in high temperature superconductor. The tools developed during this time are important, like Seamus Davis at UC Berkeley built this quantum microscope that was important to study superconductors, and this kind of equipment accelerated research. Neil Ashcroft proposed metallic hydrogen for high temperature superconductivity, and Michael Eremet at the Max Planck Institute in Germany used hydrogen sulfide to achieve again high temperature superconductivity. But it had to be compressed. This is typically of superconductivity. You have to compress these things a lot. Anyway, at this point, we had I call it the new age, the modern age, our age of superconductors. Yeah, you need enormous pressure, and then you can have hydrogen that transforms into a metal, so metallic hydrogen, that superconducts at hundreds of kelvins. So with that's almost room temperature. And so this is the age of superconducting in what they call hydrides, hydrogen-rich materials. A Chinese scientist predicted theoretically that this material, lanthanum decahydride, can be a high-temperature semiconductor. At that point, it was just a theory. Eremet, again in Germany, discovered that it is, so he proved it. And that was at the temperature of minus 23 Celsius, which is getting close to human affordable temperatures, again under very high pressure. Now, Philip Anderson theory is still not confirmed. We'll see that in some recent ideas, and we still don't know what is the glue responsible for high temperature superconductivity. Now, as I said, Seamus Davis, who is now at Oxford University, used this quantum microscope, and he claims that he proved the Anderson theory. in which case we would know what the glue is. And a few months ago, 2 months ago, a scientist claimed the superconductivity at room temperature, 20 degrees Celsius. But that's not confirmed, and he has a record of not being very thorough in his research. Okay, now quantum computing. Quantum computing needs superconductivity, so that's why that introduction. Why do we have deep learning like AlphaGo, ChatGPT, and so on? Well, ultimately because of GPUs. GPUs were invented in particular by NVIDIA for video games, but they enabled AI scientists to train these very large neural networks. So the CPU gave us symbolic AI, the GPU gave us deep learning AI. I wonder what will quantum processing units give us in the future. It could be a new leap forward in intelligent machines. In theory, quantum computers could solve problems that cannot be solved, are not feasible with today's supercomputers. For example, classical supercomputers cannot model large molecules. Think of penicillin, which is a well-known molecule with 41 atoms, and a classical computer would need trillions of transistors. So there aren't enough atoms in the universe. Modeling the human brain, 86 billion neurons and 242 trillion synapses at the latest count, that becomes more feasible with quantum computers. And today's cryptographic keys are virtually impossible to crack with today's supercomputers, but they could be cracked by quantum computers. So needless to say, the killer apps of quantum computing are exactly those three. Molecular modeling, that would be extremely useful in science. Whole brain neuroscience, that would enable us to understand, model, and simulate a lot more about the brain. And post-quantum cryptography. Let's start with whole brain simulation. This is something that's been going on for a while. There are big projects like the Blue Brain project led by Henry Markram. It's an international project that aims at simulating the mammalian train, starting with the mouse, eventually ending with the human brain. Just to give you an idea, modeling a single neuron requires 20,000 differential equations. And a brain region requires solving 100 billion equations at the same time. The Allen Institute for Brain Science here in the United States, right now we're in Canada, aims at mapping, is mapping the connectome of the mouse. And to give an idea, in 1 cubic millimeter of mouse cortex, there are 100,000 neurons and 1 billion connections. So these numbers are colossal. Marta Zlatic at Cambridge University just published a detailed wiring diagram of the brain of the fruit fly larva. That's an organism with just 3,000 neurons. And we finally have the connectome of a living being. Now, just to give you an idea why quantum computing is so strategic, if a country had a quantum computer right now, it would be able to read all the encrypted top secret documents of any other country. So now you can imagine why all the major countries in the world, starting with the United States and China, are investing in quantum computing. If a quantum computer arrives, it will have the same impact on software that the year 2000 had. Remember, in the year 1999, everybody was panicking because all the data in the world, most of the data in the world had only 2 digits for the year, so that they couldn't encode the year 2000. But something similar would happen with quantum computing, not in databases, but in cryptography, in security. The classic discussion started really in the 1990s. Peter Shor at MIT showed that the quantum algorithm can exponentially accelerate classical computation. I will not get into the details of the specific algorithm. But a computer that can run Shor's algorithm could break today's best cryptographic methods because they rely on an assumption that he proves the quantum algorithm would prove false. We have some criteria for a quantum computer, detailed by David DiVincenzo at IBM in the 90s. I will mention only one: long coherence times. Now, quantum computing is based on the fact that two particles get entangled. Well, if they get entangled they cannot get entangled forever because they interact with the environment around them. If they get entangled only for a very, 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 very short time, that's not very useful. Russian scientists showed that topological quantum computation is a solution for the problem of decoherence. So mathematicians in the 90s were discussing all the foundations of quantum computing. And in 1997, a scientist at IBM and one at UC Berkeley built the first quantum computer that only had 2 qubits. The qubit is the equivalent of the bits of the computer, 0, 1. And in 2001, one of them at IBM built a 7-qubit quantum computer. That it was the first computer to execute Shor's algorithm. Then since then, we've had records in quantum entanglement. I will mention just the recent ones, that somebody in Germany entangled 14 photons. Somebody in Australia achieved coherence time of 2 milliseconds. It sounds short, but you can do a lot of calculations in 2 milliseconds. And somebody in Austria entangled 2 ions over a distance of 230 meters. So there is yearly progress in these things. In terms of building actual computers, more than computers, these are really just processors, brains without a body. IBM built a 50-qubit quantum computer in 2017, but the state is preserved only for 90 microseconds. In 2018, Intel introduced the Tangle Lake that had 49 qubits. Google introduced Bristlecone, and IonQ became the first commercial quantum computer and used technology trapped ion, which is the most common still today. In 2019, this IonQ became the first public company, publicly traded in Wall Street. In 2019, also it introduced an 11-qubit quantum computer that was deployed on Microsoft's cloud, so you can claim that's the first practical use of quantum computing. And IBM introduced a commercial quantum computer also in 2019. The big news in 2019 was when Google's Sycamore quantum computer performed a calculation in 200 seconds that would have taken a traditional supercomputer more than 10,000 years. This was big news all over the world, for example, on BBC. But actually last year, Chinese scientists performed the same computation just by changing the algorithm, by improving the algorithm in 15 hours on a traditional computer, and it wasn't even a supercomputer. So a lot less than 10,000 years. Still, the quantum computer is faster, but not that much faster. So these are announcements of quantum computers of the last 3 years. These are basically the players right now. Last year, NVIDIA entered this field. Rigetti in Berkeley and Quantware in the Netherlands, two of the startups that got funding. Honeywell merged with a Cambridge entity to become Quantinuum, which is another popular startup right now. So now IBM has actually at least 4 different kinds of quantum computers, and the Osprey is at 433 qubits. These are announcements in China. China is also investing quite a bit in quantum computers. Last year there was this news, the media loved this news. Physicists simulated really a wormhole using Google's quantum computer. Now, the number of qubits doesn't tell you the whole story. First of all, you need to know what is the error rate, because the error rate here can be very high. And then, as I said, the coherence, how long does it last? How long the quantum state lasts? So there are 2 approaches. One is the cryogenic superconducting approach. That's IBM, Google, Intel, Rigetti, pretty much everybody I mentioned before. These are qubits based on superconducting circuits of trapped ions kept at a temperature near absolute zero to take advantage of superconductivity, basically. The photonic approach is a different approach. And in this case, the qubits are based on photons, and they can operate at room temperature. They don't require absolute zero temperatures. The other advantages is that qubits based on photons have longer coherence because they interact weakly with the surroundings, with the environment. So the photonic approach can be dated back 20 years when scientists in the United States and Australia proved that it is possible. Then in 2015, PsiQuantum was formed specifically to invest in this field. In 2016, Xanadu in Canada introduced a quantum computer based on the photonic approach, and then China and England, France, Germany. So this technology has been tested in different countries. I'll mention that last year Intel demonstrated the highest yield to date of silicon qubit devices. Why is this relevant? Because if you use silicon, if you can use silicon, you can use the entire production chain that is currently in place to build chips. So that would simplify things a lot. Quantum computing is based on spin. Spin qubits in silicon is a promising candidate for large-scale quantum computers. Remember that we can achieve. So I said 400 qubits. That's still a very small number. So if we want to reach large-scale quantum computers, we need a different approach, and using silicon atoms could be the solution. It's not trivial because we have to do something to the silicon that is normally used. Now, at the theoretical level, there's a lot of research. There's a lot of announcements every single year. It's hard to catch up with what is going on. First of all, a distinction between holes and electrons. In an electric current, you have electrons, and then you have an electron and a hole, an electron and a hole. Electrons are spin, their spin is half. Holes have a spin of 3/2. So, and they're not real particles, but that's the positive charge in an electric current. So their spin is different, but you can create qubits also with a spin of holes. And what's the advantage? Way faster. They have a longer lifetime, and they can theoretically perform 100 million operations per second. And so you will see announcements like the one I mentioned there. Switching in with holes is a lot faster, 2 orders of magnitude faster than with electrons. And of course, trapped ion quantum computers are easier to make. That's why we have them, but they are much slower. This Dominic Zumbul in Switzerland is one of the scientists who is working on A, holes, and B, silicon. So you put together these two ideas, and you could get a new kind of quantum computer. 2 months ago in Las Vegas, there was a major meeting of physicists, and you can see I extracted some of the talks. You can see that there were a lot of papers talking A, about using silicon, and B, using holes instead of electrons. I will mention Guido Burkhardt because he's a pioneer of this research. He has published several interesting results. Yeah, so silicon quantum computing is obviously very interesting. In Australia, there's a center that has been working on silicon quantum chips, and last year demonstrated a quantum computer integrated circuit. These are, just to give you an idea, these are some of the people working in this field around the world. So there's very little that you can do in practice with quantum computers, but there are a lot of research centers working on them. Now don't remember why I mentioned these two specific scientists, Jason Petta, Princeton. Long-range coupling of 2 spins separated by 4 millimeters using microwave frequency photons probably was a major achievement at the time. And Chris Morrow is with the IonQ. They built the first quantum logic gate. I don't think it's 2000. That's maybe it is 2000. And quantum entanglement between 2 widely separated atoms. So these are major achievements in the history of the science. And IonQ, as I mentioned, is the first quantum computing startup that went public. Again, very recent announcements. Just weeks ago, these scientists in Los Angeles, HRL Laboratories, announced this method, according to which the qubits can be used for any kind of quantum computational application. And IBM, as I already mentioned, has introduced a 433 qubit quantum computer. Quantum error correction remains a major topic of research. It is not a detail. It's actually one of the most important properties of quantum computers. Alexei Kitaev predicted in the 90s the topological quantum computer that would solve the problem, but nobody has ever built one. Google, 3 months ago, published a paper claiming that they can reduce the error rate by increasing the number of qubits. So this is a very recent idea. These are startups in the Bay Area. Venture capitalists in the Bay Area have been investing in this field, although it's still modest investment. Now, as I said, from the point of view of governments, the appeal of quantum computers is that they would break the existing, most efficient cryptographic algorithm. The NIST is the National Institute of Standards and Technology in the United States, and they've been concerned with this problem for at least 10 years. They launched the PQC project 2012, It's a competition to see who could build basically the most secure quantum computer. 4 winners were chosen last year, and I will briefly show who they are. I'll mention that Amazon, IBM, and Google are already implementing this quantum safe algorithm. So we already have a way to avoid a catastrophic collapse of security. Crystal Kyber, developed by scientists in different parts of the world, but notably by IBM. And then the others, I mentioned some of the original papers. Crystal Kyber is probably the most famous. Is part of is based on a mathematical idea that has been around for a while. Been around for more than 20 years. All the Regev came up with through Triple System in 1996. In this field, Vadim Lyubashevsky of IBM, appears frequently. So one of the key people in this field. These are the other 3 algorithms that won best prize. All of them based on mathematics that is not very recent, actually. People start talking about the quantum internet. It's probably too easy to talk about quantum internet, and too soon, way too soon. The idea is that quantum information could be stored and delivered by photons. And I mentioned 3 studies, Feng Pan at Stanford, then the group at Cambridge University, and the group in Switzerland that are working on these ideas. Okay, let's move on to batteries. This will be quick now. I just want to say a few words about batteries and then about nuclear fusion. All I have to say really is that there's research ongoing beyond lithium, the current lithium-ion battery. Here I mentioned 4 startups. Lighten works on lithium-sulfur battery. QuantumScape works on lithium metal batteries. Nanodiamond works on beta voltaic batteries. And Natron works on sodium-ion batteries, and a lot of companies, especially in China, working on sodium-ion. Why? Because sodium is found in salt water. Plenty of salt water in the world. Particular research I want to mention is on silicon anode batteries. Of course, the moment you hear silicon, we can use the existing fabrication technologies. So these are startups working on this technology. Recent announcements, just weeks ago, Vienna University of Technology demonstrated their oxygen ion battery, and Saltjanks in Wisconsin demonstrated, I think it started selling the salt water battery again. Plenty of salt water in the world. It's also interesting that beginning to see startups in the field of carbon capture and storage. It's Carbon Clean built a carbon capture facility in India in 2016. As far as I know, it was the first such facility. And then 2 years ago, Climeworks built one in Iceland. Heirloom, just recently in San Francisco, built the first, based in San Francisco, built the first direct air carbon capture facility in the United States. And Living Carbon, also based in San Francisco, is genetically modifying trees to create super trees that absorb more carbon from the air. And lots of startups working on these ideas. even more briefly about nuclear fusion. Many approaches to nuclear fusion. This was another dream technology like quantum computing until recently. In 2021, Sam Altman, famous as CEO of OpenAI, invested in one of these startups. Last year, Google invested in another startup of nuclear fusion. So a sense, a feeling that is coming closer to reality. And especially few months ago, Lawrence Livermore Lab announced that they produced more energy than they used. Nuclear fusion requires high power lasers that use a lot of energy. So the previous experiments produced energy, but they consumed more energy. And this is the first time that more energy was produced than was used. And this is Annie Kricher of the Lawrence Livermore Lab talking about it at a Stanford event that I organized recently.